Okay, very quickly. Do you guys remember what we were talking about, right? So I'm sort of quickly going to go over the idea of a generative model. But before that, here's what we had. We were speaking of trying to generate data, right? And when we are trying to speak of generating data like data from like facial images, what is it we are really speaking of? We are saying that facial images have some distribution. And if I draw a sample from this distribution, what comes out is going to be a face. And so our idea is to try to learn this distribution. And so that we can draw samples from it. And when we draw samples from it, different samples are going to be different faces, right? Right? So that's the basic idea. Is that making sense to all of you?
I love the drawing.
A lot of drawing, but it's all right. But besides that, okay. Now here's the problem. The problem is that if you look, data are faces, for example, are in some 1 million dimensional space. If you have a 1,000 cross 1,000 pixel image, correct? In this 1 million dimensional space, what does the distribution look like? We don't really know, right? It's a very high dimensional space. The distribution can have some ugly shape. It can have high probability. The high probability regions are unknown. The low probability regions are unknown. We cannot really say what the distribution looks like. So we need some way of characterizing this distribution, and we need some way of drawing a sample from this distribution. Unfortunately, it's very unlikely that this distribution has any kind of a shape that makes sense. So given this, can we use a neural network to characterize the distribution? And can we use the neural network to draw samples from it? That's the basic problem. You guys with me?
Yes.
Yes. Okay. Yeah. So this is easy. So how are we going to model this distribution? We will say we're going to look at it. Now, typically, what kinds of distributions are you guys familiar with? Can you give me a name of a distribution?
A Gaussian.
A Gaussian.
Poisson distribution.
Poisson distribution, uniform distributions, all kinds of distributions, right? Now, suppose I give you a collection of data. How do you estimate the distribution of the data? Anybody remember?
You compute the KL divergence between.
So first you're going to assume, suppose I have some distribution. If I plot the histogram of the data, let's say the histogram looks something like this, right? Then you're going to assume that this data kind of looks Gaussian. So you're going to try to fit a Gaussian to it, right? But then there are many different Gaussians you could be fitting to the same data. So what you will do is you will consider all the Gaussians, and you have the data P of X, and you have the Gaussian, which I'm representing by this theta, and you're going to find the Gaussian which maximizes the likely probability of this data. So this is your maximum likelihood principle for estimation, right? Everybody familiar with this? Blaine?
Yeah.
Right. Okay. So we'd like to use the same principle over here, but first, for this, we need a form for this distribution, and it's highly unlikely that that faces have anything like a Gaussian distribution or any well-known form of distribution. So here is what we're going to be assuming. Faces are structured, right? So that means they don't fill up the entire space. They lie in some close to, by the very definition of being structured, it means that the effective dimensionality is lower than the dimensionality of the space. The number of possible variations is small compared to the dimensionality of the space. Is that making sense to you guys?
So it's like they are likely to be lying on some plane in a higher dimension.
or some curved surface, right?
Okay.
Or some close to some curved surface,
Okay.
right? But even on this curved surface, they're going to have some kind of a distribution, right? And the distribution is not necessarily, so if I were to flatten the surface, then on this surface too, the distribution could be anything, right?
Yeah.
Make sense?
Yeah, so
But
this
then
is a manifold here, right?
it's a manifold, right?
Okay, yeah.
But then you have the ability to stretch and shorten this thing such that things get lumped up of non-linearly transforming this such that on the surface, eventually the distribution is Gaussian.
Right.
Okay. So the model, so the generative model that we're going to have is this, that in order to generate a phase, there's some magical underlying process. So when I'm thinking of a Gaussian, when I see Gaussian data, then I'm thinking of this magical underlying process, which occasionally dips its hand into a Gaussian distribution and yanks out a vector. That is the generative process for Gaussian data, right? It's a very simple generative model. So I want a generative process for the phase data. So the generative process I'm going to assume is that I have this guy, and this guy yanks out a Gaussian, but he doesn't just give me a Gaussian, he sort of transforms it through some nonlinear function. And that nonlinear function is what gives me phases. So this is my generative process. Then you add some fuzz to it, and that's what gives me phases. So is this concept of a generative model making sense?
Yeah.
So this non-linear function here is basically the decoder, right?
This is our decoder, right? And
Okay.
basically, right? So that's but then if you look at it from a mathematical perspective, what's happening? That this Gaussian is basically some nice isotropic structure in a high dimensional plane. So if every point in this plane were to be put through this nonlinear function, the nonlinear function, as we saw, is going to sort of warp that plane and put it in make it some other bent surface in the higher dimensional space, right? And so basically you have this decoder which warps this plane and puts it in a high dimensional space. And if you have any distribution of points on this plane, it's now going to be a distribution of points on this surface. Is that making sense?
Yes.
Yeah.
And then
Yeah.
when you add fuzz to it, it's going to have some distribution which is slightly off the plane, right? And so our generative model says, that the distribution of faces is actually some fuzz around a plane, okay, around a curved surface of some
Yeah.
dimensionality.
I'm
And
not really following why that is the case. So why do we need to get off the plane to generate faces?
so basically, it doesn't necessarily have to be, the plane is smooth. The point is, if I take a face and modify a pixel a little bit, it's still going to look like a face to you, right?
Right?
So if I can take a fixed face image, I can modify individual pixels in the image, every single pixel a little bit, and it's still going to look like a face.
Mm-hmm. Yeah.
Correct? So which means that the actual face images have dimensions and have components in every dimension.
All right. Yeah, I see. Okay.
Right. So you model it as having a little bit of fuzz around the surface. The main structural component stays. If you vary things around it, it's still going to be a face.
All right. Yeah. Thanks.
Does that make sense?
Yes.
Okay. So once I model it this way, then I need to have, what does the problem become? The problem is, how do I find this function? I'm going to say, I can't model it directly over here because this structure is unknown. The shape of this surface is unknown. So I'm going to say, I'm going to warp a plane into this shape. And specifically, I'm going to warp a plane such that there's a uniform Gaussian distribution on this plane. And when I warp it, that plane is going to become a surface, and this distribution is going to get transformed to a new distribution on this surface. And if I add a little fuss to it, that distribution looks like the distribution of faces. Is it making sense?
Yes.
Yeah.
Right? Okay, beautiful, right? And so now the problem is, if I have this kind of a structure, how do I, if I give you a collection of faces, I know the collection of faces has been drawn from this distribution, right? So the collection of faces has been drawn from this distribution. How, given only the samples that have been drawn from this distribution, I can actually find out what this function is. Is that making sense to everybody?
Yeah.
So that's how do I make the encoder now? Or
So the point is this, a face is just a point over here, correct?
yeah.
So I'm giving you a collection of points over here in this outer space, right?
Yeah.
Now, these points are basically lying around some fuzz of a surface,
Yeah, I see. Yeah.
correct?
Yeah.
And each point over here, according to our model, has or corresponds to some point on the plane itself to which noise has been added, right?
Mhm.
And then corresponding to that plane, there's some point over here, right?
Yeah.
And this point has been transformed through the nonlinear function to generate this point. And from that, you've got this new point. Is that making sense?
Yeah.
Yeah.
So the nonlinear function in the other direction is the encoder.
This is still, I'm still speaking of the generator model, right? That's
Okay.
this
Okay.
guy, right? Yeah.
Yeah.
So this clear, Blaine, UA, Shima, Jinkon,
Yeah.
right?
Yeah, it's clear.
Okay, so now if I want to learn this function, I need to know which point on this plane went into the function, which point it became on the outside, correct? And if I know it
Yeah.
for every one of my training points, I can learn this function.
Yeah.
That making sense?
Yes.
Yeah, it does.
Right? Yeah. Everybody, is that making sense? Shima, Jinkon. Right. Okay, so Shimiao. Sorry, I missed you, mispronounced your name. Okay. So, all right. So assuming that all, so what does the problem become now? The problem simply becomes for every face point, right? We have to first find these guys. And then from those guys, we have to estimate this one, correct? So for every one of my training faces, suppose I found the corresponding point on the plane and the corresponding point over here, then I'd have a bunch of points on this plane and a bunch of points out here, and I could use those two to learn my transformation function. Thereafter, if I wanted to generate a new face, I'm going to draw a Gaussian sample, meaning a sample from a standard Gaussian on this surface, pass it through this function, which will give me some point on this surface to which I can add a little bit of the noise, and I'm going to get a face. In fact, even if I don't add the noise, this is going to be like a smoother, blurrier version of the face. Is it making sense?
Yeah.
Right? So this is the whole thing. That's the entire distribution model. This is the model we are trying to learn. Okay. Now the problem is this. We don't know these two guys. So these two guys also have to be estimated. Right.
Yeah. So the encoder will produce the first guy, right?
So the point is, how is the encoder? So now this is the problem is we don't know. To know this guy, you would need to know the sheet, correct? So that you can find what the closest point is. Right? then you would need to know this guy. And then you'd have to pass this thing backwards through this to find out what the corresponding point over here was. That's the way you're going to have to find out Z and Y, correct? Is that making sense? Oscar?
Yes, yes.
Yue, Shimiao, Blaine, this is making sense.
Can you re-explain, like, what do you mean by going back from the right to the left?
So if I from the face, if I knew the plane, I could find the point on the plane, correct?
Yeah.
Then I could sort of put it through the inverse of this function, assuming the function is invertible, and find the Z that went through the function to generate this point.
Oh yeah. So it's like, given a face generated by this procedure, you go back.
Yeah, and so now I can use this to find out every one of these points and every one of these points, and then use those. But then I can estimate the model. But this is kind of a chicken and egg. To find everything that I need everything, right?
Yeah.
Okay.
Yeah.
So here's what we are going to do. I'm going to come up with an initial guess for this function. Okay. I come up with an initial guess for this function, and then this initial guess for this function. So we need to find out which point on the Gaussian, on the input space. It has a Gaussian distribution, but in the input space corresponds to which face, right? And also which point out here corresponds to which space, because this input space is being transformed to this curved surface. So these guys are off the surface. This variation has been induced by this additional additive noise that we had outside, right?
Yeah.
Right. So we need to know these two guys. Everyone with me? Okay. So here's what I'm going to do. I'm going to come up with an initial guess for this nonlinear function. Then I'll take this function over here, all right, hypothetically, and I transform it into the, take this input space and I transform it and I get a curve, okay? Now that I have a curve, for every training data point, I'm going to find a point on this surface. And then I would get it for every one of my training data points. I can put all of these guys back through this, find the corresponding Z's, right?
Yeah.
And then use these Z's and these points and re-estimate this function. Each time I do it, the fit is going to keep getting better and better and better.
Yeah.
Right?
So you project them onto the manifolds, and then you try to model the distribution on the manifold.
So what I'm going to do is there's no distribution being modeled at all over here, is there?
The distribution of the input data?
So all I'm saying is that, we haven't even gotten to distributions.
Oh, okay.
What I'm going to do is I'm going to project each point onto the manifold,
Yeah.
right? Then take it back and find the corresponding Z somehow.
Okay. Yeah.
Okay. And I do this for every one of my training points.
Yeah.
And now I have a collection of Z's and a collection of, let me call these X hats, right?
Okay.
And from this collection, I can go back and relearn this function, correct?
But is there a target, like for a way to map them onto Z? There's no constraints on any mean or variation or something there.
At this point, not yet, right?
Yeah.
Okay. So I'm just giving you a high level view.
Yeah.
Okay. So is this making sense to everybody?
Yeah.
There's one question in the chat.
So we need to find out which point. That was the first question. Was there a second? There isn't a second question, is there? No. So I already answered Jinkon, right? Okay.
Oh, yeah.
So far so good. And that was what we were doing out here. So what we said was the data are distributed around a nonlinear manifold in high dimensional space. And to generate data point for this class, you must select a point from this manifold and add some noise, but skip the noise, okay? Assume that's exactly on the manifold for now. And we found, so basically, that the decoder of an autoencoder basically transforms this low dimensional latent space to this curved surface in the output space, right?
Yeah.
Correct? And so one would assume that if I could just train an autoencoder. Now, what is the inverse process? So the autoencoder gives me both parts. It tells me how to go from the phase to the latent space. So it gives me the backward function, right?
Yes.
It also gives me the forward function. Right? Remember, from here, in order to, I had to go from here, I had to go back and get the z's, and then use these z's and y's to figure out how to go from z to y, right?
Mhm.
Or x, or x, whatever I'm calling them. So, do you see how that relates to this?
So when you're going forward, you are using the decoder, and when
So
you're going back,
basically,
you are...
so from z, I'm going through this nonlinear box, and it's coming up to some x hat, to which I'm adding noise, and it becomes x, right? This is what we had. So assuming I somehow figure out how to go from x to x hat, I need to go from x hat to z, right?
Right.
Correct. So I need an x hat. The inverse process of this forward box is the one that goes to z. Right.
Yeah.
This is the decoder, but the encoder is just the inverse of the decoder. We know this.
Yes. Yeah.
So you guys with me, right?
Yeah.
So then once I do this, then for every x hat, I'm going to have a z. For every z, I have an x hat. From the z and x hat, I can estimate d. From x hat and z, I can estimate the e, correct?
Yeah.
Okay, so that's the rough level. But then there are many ways of transforming x hat to z and z to z back, x to z and z back to x. And it's not a unique solution. But then we have an additional constraint. The additional constraint was that we wanted z to have a standard Gaussian distribution, right?
Yeah.
Remember? So this conditional business was kind of spurious. It was not necessary. I confused everybody. That was my bad. Okay. So here is the situation we have. I need to find for every x, I need to find the z. I need to find the x hat, which is on the plane. I need to find the z. If I knew these two guys, I can find the decoder, right? To find the z, I need the encoder. So if I knew the x and the z, then from that I can find the encoder. Then I can use the z's and the x's to find the decoder, correct?
Yeah.
Everybody with me?
I'm only not following on how we found the X hat. Sorry.
So I haven't told you yet,
Oh, okay, then I'm following.
right? But assuming you could project it onto the surface, right? And then I need to impose an additional constraint on z. The additional constraint on z is that z must be a standard Gaussian, right?
Right.
So if I want to make a random variable standard Gaussian, then z is simply the encoding of x. And we know from the maximum likelihood principle that if I want to find the parameters that make my data, so I have two possible choices in the maximum likelihood estimate. I have my data histogram, right? And then I can move my Gaussian around till it fits the data perfectly, right? That's the argmax theta p of x semicolon theta. Remember, this is what the maximum likelihood estimate did. But then instead of moving the Gaussian, if I'm given the option of moving the data around until the histogram of the data best fits the standard Gaussian, that too works, right?
Yeah.
Right. And so in that case, you're finding the maximum likelihood estimate of the transform that transforms this data into a standard Gaussian distribution.
Oh, yeah, yeah.
Correct? It
Yeah.
works both ways. Right. And so because it works both ways, I can actually say P of the encoding of X semicolon theta as given by a standard Gaussian must be maximized. Right? Or I could put a
And what
log
is-
over here and it's the same thing. This is
Oh,
making
yeah, and
sense?
the N stands for the normal distribution.
N stands for the normal distribution, right?
Okay,
And this is
yeah.
the encoding. So UA, is that making sense?
So you're saying like as- so you're trying to fit the data towards the Gaussian distribution.
Instead of trying to fit the Gaussian to the data, now you're trying to fit the data to the Gaussian. Exactly.
Okay. Okay.
What is the thing before the P?
Yeah, that's a log. That's how I write a log.
Okay.
Okay. And here is the nice thing. Log of 1 over square root of 2 pi raised to d raised to whatever sigma e raised to minus half x over sigma squared, right? Or x, basically x sigma inverse x. That's your formula for a Gaussian. Sigma is a 1, so this goes away. Sigma is an identity matrix, so this goes away. So this simply becomes log of, I'm writing at an angle because my screen is at an angle, 1 over square root of 2 pi raised to the dimensionality of the data, e raised to half of norm of x squared, right? This is the probability distribution for a standard Gaussian. In our case, this is going to be the encoding of x semicolon theta, right? Whole squared.
Yes.
If I take a log of this guy, right, then the log n, this becomes a constant, it goes away, log n e cancel out. You're just left with half of the encoding of x semicolon theta whole squared, right?
Oh, yes, I see.
Okay.
Yeah.
And
Yeah.
so basically what this means is that when I'm trying to maximize the log likelihood of the data against a standard Gaussian, it's the same as minimizing the negative of the log likelihood, right? Which is the same as minimizing 0.5 times the norm of z squared. 0.5 is a scaling factor. It's just this guy. So minimizing, fitting, modifying theta such that z fits a standard Gaussian is like solving this problem, correct?
Okay.
Yeah.
Yeah.
Everybody with me? Shinyao, Blaine, Yue.
Yeah. So Z here is the same as the encoded output, right?
Correct. Z was so Z here is basically this one, right? Sorry, why does this thing go around? Z was this term that went into the decoder,
Okay.
right?
Okay.
Got it?
So
And so-
minimizing the norm is enough to map it to a standard Gaussian.
Exactly.
Okay.
Squared norm,
Oh, yeah.
right? And so you ended up with, I want to go from, I want to, given Z and X, I want to find the encoder. Given Z and X, I want to find the decoder, right? But I can map it all off as saying I go from X to Z and Z back to X. So I want to minimize the error between X hat and X. That's the autoencoder, while trying to ensure that Z is also a standard Gaussian.
Yeah.
So, Professor, I have a small doubt. So
Yeah.
here we are, the encoder is actually transforming the input data no matter what distribution it has into a standard Gaussian, right?
Correct.
So what if like there are like higher dimensions in input data and everything can't be modeled into a standard Gaussian. So
So what is
would
going to
that-
happen? Tell me.
So there'll be more error.
It's just going to, so basically if your input data is, so the assumption that we are making is X, we're already making the assumption that X lies close to some, come on, please don't do it, right? So because of the maximum likelihood principle, we are making the assumption that X lies close to some manifold, right?
I see,
So,
yeah.
so what is the best if you are trying to maximize the likelihood of the data? What is the info? Which surface are you likely to convert to the plane? Would you be converting this surface to the plane? Something like this. Z is the plane, right? The latent variable plane. The
Yeah.
encoder is taking this curved surface and converting it to the latent variable hyperplane, right?
Yeah.
It could be converting any of these guys to this hyperplane, right? Of
Yeah.
all of these, which one is it most likely to convert to the hyperplane? If you're trying to do a maximum likelihood fit.
The curve closest to the data, the black
The one that's in the data. Is it making sense to the rest of you guys? Do it?
Yeah, yeah,
Oscar?
yeah, yeah.
Right?
Yeah, so the line through the data is X hat, right?
So the line through this data is X hat, right? So
Yeah,
basically the encoder is going to, the maximum likelihood principle sort of kind of ensures that this is the surface that becomes Z,
Yeah.
right? And also sort of ensures that it's sufficiently warped that the things move around over here so that in the Z plane, they are uniformly distributed.
Mhm.
Right? Everybody with me? Siddhartha?
Yeah, Professor.
Yeah.
So, and so that's basically our setup. This is what we had. We were trying to learn the decoder and encoder parameters while also trying to minimize the squared norm of Z. And this simultaneously learned an encoder and a decoder such that Z had a standard Gaussian. And we learned the function that mapped the curved, the plane surface onto the data curve and we got most of the distribution right. So everybody with me so far?
Yeah.
Okay.
Yeah.
So we could solve this problem, but then there was an issue. This is the issue that Oscar just mentioned a few minutes ago. And what was that?
We have X hat, but not X.
We have X hat. We don't know X hat.
Yeah, we don't know. Yeah, exactly.
We don't know X hat. If I had X, if I knew X hat, this whole model just kind of works. Right. The problem is that of estimating X hat. So, and that's what we really need to sort of deal with. And X hat, we don't actually observe X hat, we observe X, which arrives as a consequence of adding noise to X hat, right?
Yeah.
我懂了，登上去一点。
Pardon me? What was it here?
It's not me.
Okay. So, Shimia, this is the hypothesis, or this is over the entire data. But when you implement it, you'll be doing it over many batches and such. Okay. So this is the general principle, right? And so the problem is this, that we don't really know what the X hat is. And further problem is that because the noise itself, we're going to have to make some assumptions about the noise. And the noise we're going to assume is some kind of a uncorrelated fuzz that's being added. If it's correlated, then you can always modify the surface to capture the correlations. So the maximum likelihood estimator sort of, it's most meaningful if this ends up being uncorrelated, because if there's any correlation in the noise, that represents structure in the data that must ideally be captured by D, right?
Yeah, that makes sense.
Correct.
Yeah.
So this noise is uncorrelated. And so the model itself says that you're adding some uncorrelated noise to X hat.
Yeah.
And the problem is there are many different x hats that can give you a particular x, right?
Right.
Depending on the noise. So the relationship is no longer unique.
Yeah.
Right? So this is where I began to make my mistakes. But then if you look at all of these x hats over here, all of the x hats that could have resulted in this x, they're all different z's in the input space, right?
Yeah.
What are these z's? We don't really know, right? We know the overall z is a standard Gaussian, but the specific z's, the distribution of z's that could have generated this x hat is kind of unknown. Okay.
Yeah.
Now, given D, it's mathematically possible to try to come up with formulae for these guys for the conditional distribution of Z given X,
Yeah.
right? So what is it we are going to do? Here's what we're going to do. So I have this surface, and on this, and I got this particular X, right? Now I have the model over here. This X could have come from this point, this X hat, and that corresponds to this Z, right? This X could have come from this X hat, and that corresponds to this Z. This X could have come from this X hat, and that corresponds maybe to this Z. Could have come from this X hat, and maybe that corresponds to this Z, right?
Right.
Yeah.
Okay, makes sense, right? Now
Yeah.
we get statistical. So I'm going to say, I'm going to consider this guy and its Z. I'm going to consider this guy and its Z. I'm going to consider this guy and its Z. I'm going to consider this guy and its Z because I cannot be certain which of these X hats was actually used to generate Z. Right?
We're
Yeah.
still assuming to know X hat now, or that's going
We're
to.
not assuming not to know X hat because we don't have a unique X hat.
Yeah. Okay.
Correct? Right. If I had an X hat, so I'm saying I'm considering every possible X hat.
Yeah. But I
and
mean the
corresponding
manifolds,
Z, right?
like I mean the black line, like not the individual points.
So the point is, I don't need the surface. I just need to have a way of going back from X hat to Z, right?
Yeah.
Right. So I'm going to consider every possible X hat. But then if I'm considering every possible X hat, where does the training data come in? It doesn't really come in, right? If I consider every possible X hat, I'm discarding X. Right. So did that sentence make sense to you guys?
No.
Okay. If I consider every possible X hat, okay, then the point is every possible X hat is going to be considered for every training instance, right?
Yeah.
You might as well throw away the training instances.
So you have to consider X hat based on the
X.
input.
And so you won't just consider X hat, you're going to say, what is the probability of this X hat for this X? What is the probability of this X hat for this X? What is the probability of this X hat for this X? What is the probability of this X hat for this X? Does that make sense?
So X hat is going to be assumed implicitly in the conditional of Z on X.
So the X hat, you're saying I'm considering every X hat. I'm going to get every X hat, okay? I'm going to push every X hat through and get every possible Z, okay, for each training instance. Just bear with me,
Okay.
right?
Yeah.
But then when I compute my losses, the X hats that are more probable, I'm going to give it more weight. And the X hats that are less probable, I'm going to give it less weight.
Yeah.
Make sense?
So you are still considering all X hats, but you are giving them different weights based on the input.
Different weights based on the input for each input. And what is the
Okay.
weight? The weight is going to be the probability. This is the noise that was added, right?
Yeah.
Each of these noises have some probability.
Right.
right? So the weight is going to be P of X minus X hat using the noise distribution,
I see. Okay.
right? Which is the same as saying P of noise given basically P of X minus X hat given the noise distribution. So in other words, the probability of any given Z that I'm going to be using for any particular training sample is going to be the probability of Z given X, right? Which is basically this term. Probability of Z given X is the saying what is the probability of the X hat that I got from the Z using the, see the X came over here, right? X minus X hat. Is this making sense?
I understand what is J probability of J given X, but I don't quite
Okay,
get
this is the same as saying the probability of X minus encoding of Z on the noise distribution, right? What is the probability of this Z given this X? This Z became this X hat, right?
Yeah.
To which you had
Oh.
to add this noise.
Okay. Okay. So both
So the weight for this X hat, which is the same as the weight for this Z, is the probability of this noise.
Okay, so both the X hat and the noise must match to get X. So the probability are the same. Okay.
Yes.
Okay. I see.
Makes sense?
So the second probability is also conditions on the assumption of the noise distribution.
Yes.
Okay.
So guys, I have to take a brief break. I'm going to pause. So here's where we were, right? So the situation is this. We need to be able to compute this probability term. What is the P probability of any given Z for any given X, right? And then we want to weight the loss with that. How do you compute the probability of Z given X? For that, you need the Z and you need the X hat. So it's a bit of a chicken and egg problem. And if you consider the distribution of Z's for any given X, it's going to have some awkward shape. Right?
Do you need the X hat for the probability of Z given X?
No, we don't. You can bypass it all the way. We can directly try to estimate the probability of Z given X. So let's see how the whole thing works. We're going to actually use now the probability distribution of Z given X can be ugly, right?
Yeah.
Because we don't know. The set of Z's that produce these X hats can have any shape out here. Right?
Right.
Okay. So this can be ugly. Now this is where the variational autoencoder business comes in. We are going to approximate this distribution by a Gaussian.
Mm-hmm.
Making sense? Right? And
Yeah.
so what we will do is we're going to approximate this distribution by a Gaussian. And the business of a variational autoencoder is such that we're going to find the Gaussian that assigns the probabilities that are a strict lower bound for the Z's over here. To the probabilities of the Z's over here. So we won't actually get P of Z given X, we will get a lower bound of P of Z given X.
How do you mean a lower bound? A lower bound on what?
So remember, we're doing a maximum likelihood estimate of these parameters, right? Of the thetas. We saw this earlier.
Yeah.
Right? Instead of doing a maximum likelihood estimate, we will be maximizing, instead of maximizing a likelihood, we will be maximizing a lower bound on the likelihood.
Okay. Yeah.
Okay. That's a variational lower bound. That's where the variational autoencoder comes in. And so we're going to approximate this P of Z given X by a Gaussian. And we'll estimate the parameters of that Gaussian such that the overall probability distribution, the likelihood assigned to the data, is a lower bound on the actual likelihood of the data.
Yeah.
And we're going to keep maximizing it. That's where the variational autoencoder comes from. And so now the mechanics of it are kind of straightforward at this point. So the first thing we want to do, we want to get the z's from the x. Before we learn this guy, we want to get the z's, right?
Right.
So instead of getting the z's, we are going to get the p of z given x, okay? And for p of z given x, we're going to need this encoder. So the first step over here is we're going to try to train the encoder, learn the encoder, okay? So then once the encoder is learned, we're going to get the p of z given x, from which we can get some z's, and then from that we can use we're going to try to learn the decoder, okay? But it's all kind of integrated. So here is what we want to do. We want to find this encoder z that makes this encoder theta, that makes the more probable z's for any given x more probable. So what do I mean by this? For any given x, the z that corresponds to this x hat should be more probable, right?
Yes.
That makes sense, right? So in the first step, we're going to try to learn this guy such that the z's get arranged on this distribution. Again, remember, this guy is uncertain, right? The decoder is uncertain. Nothing has been learned in the beginning. So our initial guess for even this surface is going to be kind of ugly. So the x hats that are closest to this x, there's these, again, this is a zero mean Gaussian. The error is assumed to be a zero mean Gaussian. So the x hats that are closest to the x hats are going to be more likely, right?
Yeah.
So we want to learn the encoder E such that the probabilities of the z's corresponding to the x hats that are closer to x are greater than the probabilities of z's that correspond to the x hats that are farther away from x. Does that make sense? Right? And so here's what happens. But then when you're actually, again, this distribution is, you want to character, you're not going to be considering all infinite x hats that could have produced this x. That's going to be impossible because there's no way of doing an integral and computing that formula. Okay? Is that making sense?
Mm-hmm. Yeah, and we don't know each x hat as well. We don't know the
I don't know
manifold.
which x hat produced x. So as I said, you have to consider all of them, but considering all of them is going to be impossible.
Yeah.
So you're going to sample some of them.
Yeah.
Okay. And so what we will do is we are going to first have some initial estimate for this guy, which is going to give me a probability distribution of z for any x. Okay. From that, we're going to sample a z. Okay. Then we're going to pass that z through this decoder. That's going to give me an x hat. Is that making sense? So let me draw this process. At this point, all we have is x, okay? X could have come from all of these x hats, right?
Right.
Okay. So there's a decoder, D. There's the encoder, E, right?
Right.
And then we have the x, which is going to give me, from the x, we're going to compute P of z given x. We are actually computing all of the distribution of z given x. Basically, that's the step where we went from x hat back to z. That was the first step, remember?
Yeah.
Okay. So when we do this, because we already have an uncertainty over here, for this, we want to learn this guy. We want to have the encoder such that in the P of z given x, the z's that correspond to the closest x hats are more probable than the z's that are farther away, right?
Right.
Okay. So what will we do? We can't do this over the entire distribution because there are too many, there's an infinity of points, right?
Mm-hmm.
So we can sample some z's from this guy.
And is P of z given x, is that the normal, is that the standard normal distribution?
It's
or?
not the standard. P of z is the standard normal, right?
Oh yeah, P of Z alone. Okay.
P of Z given X is some subset over here, which we were approximating as a Gaussian. I remember,
Yes. Okay. 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 Yeah. Thank you.
right? From that guy, we're going to sample some Z's. And so you're going to get a bunch of Z's, okay?
Yeah.
We're going to pass all of those Z's and you're going to get X hats,
Mhm.
correct? And assuming I have a distribution for the noise, I can compute the probability for those X hats, right?
Yeah.
And then I'm going to try to modify the encoder such that all of these Z's, you want to be the more certain you are about how this guy was produced, the better off you are, because that way you're pushing the curve closer to the X. It's an integrated process, right? So what we will try to do is to try to update the encoder such that the Z sampled from this guy result in X hats that are all very close to the original X.
Yeah.
Okay. So which means that this distribution of X hats has a corresponding distribution of Z's, and you're trying to learn this encoder so that it localizes it as much as possible.
I see. I see.
Make sense?
Yeah.
Right? But then, in other words, you're going to try to maximize the likelihood of the individual samples of Z over here. Right?
That is what we're doing, right? Yeah. Yeah.
So, because we are sampling from the distribution of P of Z given X.
Yeah.
And that's where they math first. So we had to first compute what is the probability for any given Z. So we assumed that the P of Z given X was a Gaussian. And the encoder is actually computing the mean and the variance.
Mhm.
Okay. And then we're going to sample some Z's from this encoder. Okay.
Yeah.
Then we're going to push these Z's through to the decoder.
So the Q of Z and X is the same as the P of Z given X.
P or Q of Z and X is the same as the, is the P of Z, or approximation for the P of Z given X.
Yeah. Okay.
Right. So, and then we're going to try to, we want to localize the Z's, remember? So we're going to try to update these parameters such that Q of Z given X sort of focuses on towards the most probable values of Z.
Yeah.
Okay. So, but then first we need to compute the probability of Z for any probability of X hat for any Z. Basically, what is the probability of Z? So for any given Z, X hat is deterministic, right?
Mm-hmm.
So probability of X given Z is simply this Gaussian, which is going to be the noise, right? This should have been, this is X minus the decoder.
So that's X minus X hat.
On the standard Gaussian, or the equivalent of moving the standard Gaussian to have a mean of D, right?
Okay. Yeah.
Yeah. So this is like either, you can think of this as either P of X minus X hat computed on this Gaussian, or P of X computed on this Gaussian with the mean moved to D.
But shouldn't
Both are
that
the
be P of Z given X instead of P of X given Z?
So, because if I give you Z, P of Z given X is going to be proportional to P of X given Z in a Bayes rule, right? But
Yes.
if I give you a Z, then I've fixed X hat, correct?
Yeah.
So if I give you Z, this guy is deterministic.
Yeah.
So the only variability is E, which is the noise.
Yeah.
So the probability of any given X is going the same as the probability of drawing the specific E that converted D to X.
Yeah. 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 Okay.
This is X hat, right? So that's this formula, okay?
Okay.
And so if I take the log of it, we know this is what the standard log comes out to be, right?
Right.
And so we are going to try to find the encoder. Remember, the encoder is trying to push all of these Z's. We're trying to push the Z to be the conditional probabilities of z's to be very compact so that you're able to localize the z's that best capture the x hat, right?
Right.
Right. So this is what the localization is going to do. Make sense?
So how do we learn the sigma from this formula as well?
No, so we will, but right now we are looking at the encoder.
Okay. Okay.
But you'll see that the encoder doesn't even figure, theta doesn't figure in this formula, right?
Right.
The formula only has the decoder. The likelihood is computed on z, and z is a sample. So right, so now this is where, if you want to optimize the encoder, you want to find the encoder that localizes the z, we have to convert this to a function of the parameters of the encoder, right?
Yeah.
Okay, and that's what we want to do. But then what we know is that z is obtained from this as a sample from this distribution, right? Where this mu and sigma are obtained from the encoder. Which is, and the way you would do it is to draw an epsilon from a standard Gaussian, multiplied by the square root of the variance, and then add the mean. This process gives you distribution samples from this distribution.
Yeah.
Right? So Blaine, Jermaine, does it make sense?
Yep.
So that
Yes.
Yes.
everything's making sense, right? And so now that I've defined the sample z in terms of the mean and the variance, I can compute, and the mean and the variance are both functions of theta. I can compute the derivative of z with respect to theta, right? Which is the derivative of the mean with respect to theta plus epsilon times the derivative of the square root of the variance with respect to theta, right? That's just applying
Yes.
the Oscar, Siddharth, Blaine, Jermaine. Is it making sense?
Yeah. Yeah.
Okay, so I mean, this is just mechanics. You don't even have to remember it. The point is it's feasible. And so I can write this, I can write the derivative of the loss with respect to theta as the derivative of the loss with respect to z, which is simply a simple quadratic term, times the derivative of z with respect to theta, which is just this guy, right?
All right.
And so now I can use that to update my encoder. Correct? Now the next thing is I want to, so now I've got all of my z's, which I have sampled from here. I can just use the z and my x to minimize estimate d. But then what happens over here? Again, I'm going to use the same maximum likelihood principle. I want to push that surface as close to my observations on average as possible, right? There are many different surfaces, all of which could have generated x. Which surface is the most meaningful? The one that's closest, correct? Because that's what maximizes the likelihood of x, right?
Yeah, I'm confused about one little thing. I know that they're proportional, so that's not a big deal, but the P of Z given X, we said a few minutes ago that was the same as the P of X minus X hat.
Remember, it's P of times P of Z over P of X, right?
Okay, yeah, so that, yeah, okay.
So I can maximize this, and this is where, and maximize this, P of X doesn't matter.
Okay.
Okay, so this is where the interesting thing comes in. You brought up a very important point. I sort of glossed over it and basically bullshit in the lecture, but this guy, you brought up an important point. Keep track of this, okay?
Yeah.
P of Z, okay? And so, but so far for the Z, I can compute the likelihood of X given Z, right?
Yeah.
And now, in order to make the, on average, in order to make the surface as close to all of the X's as possible, I want to reduce the variance of the noise, and I want to modify the function D itself, right? if I'm of all of these surfaces, if I want to somehow push it to the surface that's closest to the X, the shape of the surface depends on D. This distance depends on the variance of the noise, right?
Right.
Right. So that, Blaine, making sense?
Yeah, yeah.
And so I want to compute the likelihood of the specific Z, and I want to maximize this likelihood or minimize the negative likelihood with respect to both phi and sigma squared. This making sense?
Yes.
Okay. And so there is the bit. I know how to maximize the likelihood of the Z's, but what I'm maximizing is the P of X given Z, not P of Z given X, right? As
Right.
Oscar just pointed out. I also now know how to estimate the phi's and the sigma, correct? But then, as Oscar pointed out, that somehow left out this term, P of Z. We were optimizing P of X given Z, not P of Z given X, right?
Yeah.
If I want to optimize P of Z given X, I should also maximize P of Z.
But P of Z is a standard Gaussian.
No, Z is the specific samples that you observed.
Oh yeah. But
So you want to maximize the probability of the specific Z that you observed as computed using a standard Gaussian. That simply ends up being, because the Z's are being sampled from this Gaussian, right?
yeah.
And if you want to maximize the P of Z with respect to the standard Gaussian, that ends up being the same as minimizing the Kullback-Leibler divergence between P of the Z given X as given by the encoder and the standard Gaussian,
I see.
right? You're drawing samples from this guy, but you're maximizing their likelihood with respect to this guy, correct?
Yeah.
So you take the log likelihood on the standard Gaussian, and you take the expectation with respect to this Gaussian, right?
Yeah.
And so this will be finding the thetas that maximize P of Z. If it's not making sense, here's what happened. If that's not making sense, take a look at this guy again, right? Let's go back all the way here. When we spoke over here, remember what we did? We wanted to maximize the likelihood of the specific sample Z with respect to the standard Gaussian, which was the same as, oh God, this is going the wrong way. Why is it? Why is this thing somewhere here? Remember this term, right? This maximize the probability of Z on the standard Gaussian, right?
Yeah.
Except now you're not drawing a simple Z, you're actually computing an entire general distribution of Z's, which is a Gaussian, right?
Right.
Remember? So you want to take an expectation of this guy with respect to the entire distribution of Z's that you had. So you could just be optimizing this term. This would actually be Z, but yeah. But so that simply ends up being, I can spend more time on it. It's not such a big deal. It's not such a complicated concept. But then if you consider the entire distribution of Z's that the encoder captures, and then you try to maximize the log likelihood of every Z that can be generated from this distribution as computed using this distribution, that simply ends up being the Kullback-Leibler divergence between the two. Does that make sense?
That makes sense.
Right. And so you got the overall objective, which is, this is the log likelihood of the data computed on the outside. This you're going to be maximizing with respect to both phi and theta. And this is the Kullback. So these two guys, and this is the Kullback-Leibler divergence, for which we have a formula between the Gaussian encoded by the encoder and the standard Gaussian. And this is the loss that has to be optimized with respect to the encoder parameter, the decoder parameter, and the noise variance. And now we have a closed form formula which we can estimate. Does that make sense?
Yes.
Blaine, Jamming, Siddhartha, Oscar.
Yeah, it makes sense.
Yes, yes.
So the logic is very simple, and it's far simpler than the garbage that I spewed in class. But anyways, just in offending myself, but this is the entire training process. So if I were to train it, and of course, you wouldn't have two separate networks over here. You're going to have one network which produces the mean and the variance. Okay, and so the entire complete training pipeline is like this. You're going to initialize the encoder and the decoder. Then you're going to sample an X from this distribution. Sample, I said we would have to sample multiple X's, right? It turns out it's sufficient to sample one X for each Z. Then you're passing that Z through the decoder and you get an X hat, okay? Then on that X hat, which is basically the decoder output, right? So for that X hat, you can compute the likelihood of the negative log likelihood of the X hat, which is given by this formula here. And simultaneously the KL divergence between this guy and the standard Gaussian, which is given by the first part of the formula over here. So you get this loss. You're going to compute the derivative of this loss with respect to phi, theta, and sigma squared, and use those to update all of the parameters and repeat the process.
So to map it here, you have the x minus d is
E.
proportional to the p of x given z, and the Kullback-Leibler divergence is proportional to the distribution of z alone.
Yeah, so it's like the Kullback-Leibler divergence is basically log of p of z, right?
Yeah. And the other term is p of x given z.
Correct.
All right. Okay, I'm with you.
Everybody with me? Siddharth, Blaine, Janang.
Yes.
Yep.
Yeah.
Yes.
Yes. So
What is the d log sigma squared doing there?
which one?
The last one in the blue.
So remember, that is this guy. When I compute the likelihood of the p of x given z is a Gaussian, right? With variance sigma squared I.
Yeah.
And so the log of the Gaussian always gives you the d log sigma squared, d over 2 log sigma squared. Actually, there was a mistake. Remember what the formula for the Gaussian is. The formula for the Gaussian is, we wrote it somewhere, it is, let me write it again. It's 1 over square root of 2 pi,
Yeah.
raised to the sigma e raised to minus whatever, right?
So that's the sigma of the noise function that we choose.
Correct. And so this, as we said, was a diagonal Gaussian where every term is sigma squared, right?
Yeah.
The noise covariance.
So we learn the parameter sigma.
Yes, and so this determinant, the determinant of the covariance of the noise is simply going to be sigma squared raised to d. So yeah, that's d log sigma squared, right?
Okay.
So when I take a square root, it's going to be sigma squared raised to d over 2. I take a log times some constant, or I take a log that's going to give you minus d over 2 log sigma squared. I think I missed it. So that's where that comes in. That comes from the variance of the noise this time.
Yeah.
It should be a d over 2, right?
I see.
So everybody with me, did everybody understand what we just did? Nikhil, you missed a lot, but did you get that? Whatever we did. Jinkun. So Frida, you missed some. I hope I didn't lose you guys completely, but most of it is going to be recorded. Right. Anyone else? Any other questions, guys? So the rest of it is as straightforward, right? Now, once you train the decoder, encoder, the actual generator is the decoder as we saw, right? And so I can use the generator to generate new samples. So sigma is you could or could not retain it. Typically, these guys, when I ask you to generate something, you're going to generate the mean of the distribution of x given z. So we typically throw it away. But if you want to make it more realistic, you'd have to sample from that distribution and add noise. That's why, when you see the pictures generated by VAEs, they're kind of blurry because you throw away the sigma part of the decoder. But if you kept it, it would probably be, it looks speckled and more noisy, but maybe more realistic. I don't know, right? And we also saw how we can use this to go from one phase to the other. For this, we would actually use the encoder. This is the mean computed for the first phase. If this is the mean computed for the second phase, if you sampled points on a continuum between these two and put them through the decoder, you end up actually getting the continuum of phases from that go from one to the other. It's very interesting. Actually, no, this goes from neutral to smiling. So the first phase is this, the second is a smiling one. If you take an intermediate phase, you get a partial smile. In the other case, you get the last one is this guy. If you take an intermediate, you get a partial frown. It's very interesting. It actually works nicely. So the guys, does everybody understand what I was saying so far? Can I stop the recording?
Yes.
Yes.